Hi and welcome back to our lecture series. I spent a lot of time to make all of this lecture video, and I don't need you guys to subscribe or like. Probably I just need you to view the lecture and study. But anyway, thank you very much for viewing this lecture so far. So let's begin. So this lecture is lecture 21. It's about the counters. Previously we viewed the we study about the registers, right? And the next element that we will study is the counters. So very similar to registers. Like registers basically store memory and it reacts on a clock pulse. What are counters anyway? Counters are basically to count, right? The main purpose of counter circuit is for counting. So there's a textbook definition for it. A counter is a register that goes through a prescribed sequence of state upon the application of input pulses. Okay, so you recognize there's two keywords here. The first keyword is registers. Okay, that means counter by itself is just a register. That means it's a group of D flip-flop. Each D flip-flop store a specific information. But here the state of this group D flip-flop will change in a prescribed sequence. You can design a sequence. And the change is upon an application of input pulses. Why do we use the word input pulses? Commonly, we work on clock pulse, right? Clock is one of our input. So these input pulses can be the clock pulses, but also you can have an external source of input for this input pulses, and we will discuss about it later in this lecture. So what are the different types of counters? So in this lecture here, we will go through the main two types of counters. We have the ripple counter. Okay, so the ripple counter is the definition of that is the output of the previous flip-flop will be used to trigger subsequent flip-flops. In other words, the flip-flop operated independent to a clock, so it doesn't need a clock. Okay, a synchronous counter is on a flip-flop triggered by a common clock. So this one doesn't need a clock. This one needs a clock. This one why is called ripple because the state of each flip-flop will change rippably. Okay, so the state of flip-flop 1 change and it trigger the change in the state of the next flip-flop and it trigger the change in the state of the next flip-flop. Okay, that's why it's called ripple. Synchronous, everything change at once by a common clock. And there's also other type of miscellaneous counter, and we will discuss a few of them later in this lecture. So first of all, let's just build some counter. Okay, so let's build a basic 3-bit binary counter that increments by 1. Okay, on each clock pulse. So when you hear the word, okay, increment by 1, that means it increase by 1 every input pulse. When you see the word each clock pulse, that means this is what type of counter it is. Is that ripple counter or synchronous counter? It's the second one, right? Because you need the clock to do it. So step 1, let's define the number of state or of the state transition. Okay, so if you have a 3-bit counter, you count from 0, 0, 0 on the way up to 1, 1, 1, right? So you increment by 1 every time the clock pulse. When you reach the largest number, it go back to 0, 0, 0. in the next state. So here is the state diagram. Okay, why don't I have any input or output here? Because I know that every clock cycle or clock pulse, it will move to the next state. So technically, I just work on the clock pulse, so I don't have an external input or output in here. So if I have the state diagram, remember, I can have a state table. So I have a present state and the next state. So it's very simple, right? The present state and the next state is just the present state increment by 1. So if you have 0, 0, 0, and you have the next state is 0, 0, 1, and so on until 1, 1, 1, it will go back to 0, 0, 0. Just following this circle right here. Alright, so if you have present state, next state, maybe you can remember you can implement some flip-flop inputs in here. So let's use T flip-flop in this example. Okay, if we use T flip-flop, and remember what is the key thing about T flip-flop? T flip-flop have only one input, either 0 or 1, right? You can supply either 0 or 1 to the T input. If you supply 0, the output will stay the same, right? I mean the state of the flip-flop will stay the same in the next cycle. If you supply a 1, then the output of the flip-flop will flip. Okay, so 1 is flip, 0 stay the same. So now you just have to compare the present state and the next state. You see that A0 flip, the other one stay. So you have this one to be 1, and so on. You just basically scan for which one flip and which one stay. So you fill out this table right here. Okay. So now you have your full table, present state, next state, and flip-flop input table. Remember what to do next. You can write the flip-flop input equation. So you can assume your you can have your present state, okay, as your input. You can have your present state as your input, and you can have your flip-flop input value as your output of the truth table. Then you can construct your K-map. Okay, so in this case I scan for A2, A1, A0, and I will solve for TA2, which is this column right here. I fill the column, I use this column to fill out this K-map. I do the grouping, and now I have the equation TA2 equal A1, A0. I'll do the same thing for the next column, TA1. Okay, so use this, fill out the K-map, write down my equation, TA1 equal A0. Likewise, I use this column, and this one is pretty easy. You see, everything is 1. So, of course, TA0 BB equal 1. You don't even need to do the K-map, this piece of cake. So now you have all of the input equation. Now you have all of the flip-flop input equation. You can go ahead and construct your circuit. So this is a synchronous 3-bit binary counter, counting from 0 to 111, increment by 1 each clock pulse. Okay. So what about ripple counter? So ripple counter are not reliant on the clock to count, so you don't need the clock. But if you don't need the clock, you will need some other input. Let's say you can supply another input that is called count. So each time this input pulse, you increment the state. Okay, you increment the count number, and I will go through that a little bit later. So this flip-flop output transition serves as a source or trigger the other flip-flop. So the flip-flop is not triggered by clock, but by the transition occur in other flip-flop outputs. So this is the reason why this type counter is called ripple. One flip-flop transition in the output, it triggers the transition in the other flip-flop. Okay, so the state of one affects the state of another. There are two primary examples for the ripple counters. The normal binary ripple counters. This one can be built by using T, J, K, or D flip-flops. Count 1 at a time in binary when the count in input has a positive edge occur. When I say positive edge, of course you can also design a negative edge system, but let's stick with positive edge for. You can design a negative edge system. Yeah, so basically it can either positive or negative edge, depend on what's your design. But another term for this is every time the clock pulse, you have a count. So case study for this, if you have a 4-bit binary ripple counter, if you start from 0, okay, which is 0, 0, 0, you increment by 1 in each pulse. After the count go to 15, which is 1, 1, 1, 1, it will go back to 0 and repeat. So another case is the BCD Ripple Counter. BCD basically is similar to binary, but it's only represent from 0 to 9. So it will count from 0 to 9, then it will cycle back to 0. Okay, so it's the same thing. Start from 0, increment by 1 each pulse, and after the count 9, go back to 0 and repeat. So first of all, let's examine the 3-bit binary ripple counter. So you have let's use the same state diagram from our last example. Okay, so with this state diagram, I can also write down the series of number. Okay, so this is the counting direction from 0 to 1, 1, 1. Okay, so now you recognize I have 3 different columns, right? 3 different digits. Each of them I can use a flip-flop to represent its value, either 0 or 1. So now I want you to start examining, okay, each of these. So if you see in here, the transition of this is basically just 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and go back to 0. So every time the input pulse, this one will flip no matter what, right? Every time the input pulse, this one will flip. Okay. So this A0 value will flip every time, every single input pulse. Every time the input pulse, this one flip. Now I want you to examine A1 based on A0. So now take a look at this. This one, it flipped, but not every single input pulse. Okay, so let's try to figure out when does A1 flip. So if you take a look in here, now this sequence 0, 1, 0, 1, 0, 1, 0, 1, it looks like a clock, right? It looks like a pulsing sequence. So you can see that every time A0 pulse, or more precisely, every time A0 go from 0 to 1, then the value of A1 flip. So you can see that every time A0 goes from 1 to 0, A1 flip. Okay, so you can recognize that. So it's from 0 to 1. I mean, so every time A0 goes from 1 to 0, value of A1 flip. And same thing with A2. Okay, every time A1 goes from 1 to 0, A2 flip. Okay. With that knowledge, now you can build your circuit like this. Okay. I will explain why. First of all, you have 3 T flip-flop, and remember the key thing of T flip-flop is it does 2 things, either hold or flip, right? Either it holds value or flip its value. So let's examine the first one, the first T flip-flop in here. Actually, let's first examine the whole 3 T flip-flop. The key thing is you need to hardwire logic 1 into on 3 of these. Okay, the reason why is you want all of them to flip. You want all of them to flip depending on like the state of the other one, but you don't want to hold, you just want to flip it. Therefore you hardwire the logic 1 into on 3 T input of this 3 T flip-flop. Next, take a look at this. Okay, the count input is wired to the clock. The count input is wired to the clock of this circle. Okay, so you can see that the count input is wired to the clock of this T flip-flop. And remember, when does the value flip? The value of A0 or A1 or A3 flip when the previous value goes from 1 to 0. So it's the negative edge, right? So that's why there's a bubble in here. That's why there's bubble in here, and that's why there's a bubble in here also. So if you supply a count in here, let's go through one example. If this one flip, okay, if this one go from 1 to 0, okay, if this one go from 1 to 0, then you will flip A0. Okay, you flip A0. So if you flip A0, either you can have it go from 0 to 1 or go from 1 to 0. Okay, so now if A0 go from 1 to 0, it will trigger the flipping operation of the next T flip-flop, okay, and cause this one to flip. And if this one flips, so either it go from 0 to 1 or 1 to 0. If it goes from 1 to 0, now you trigger this one to flip. Okay, so that's how it works right there. You can also build your 3-bit binary ripple counter with a D flip-flop, but the main concept is the same. You need to make sure that you have a flipping operation for the on 3 flip-flop that you have in here. So in order to supply a flip operation, you want to feed the complement output of that D flip-flop back to its input. Okay, so if you do this, you provide a flip operation, and the same thing remains. Okay, the same thing remains. Okay, next we will go through the BCD Ripple Counter. So the concept of Ripple Counter is still the same for BCD Ripple Counter. You want to examine each flip-flop, okay, you want to see how the previous flip-flop will affect the state of the current flip-flop, or how the current flip-flop will influence the state of the next flip-flop, okay. So, but for BCD Ripple Counter, basically this type circuit doesn't count from 0 to let's say 15 for a 4-bit binary. This circuit count from 0 to 9, same every time, okay, count from 0 to 9, then repeat. So because it counts from 0 to 9, the smallest number of bits for a binary system that you need is a 4-bit system. Okay, so you need 4 flip-flops to represent those values. So you can use a count pin or a count input, and you can pose it to basically run or to change the state of the first flip-flop clock. To run it into the clock to change the state of the first flip-flop. So similar to the normal binary ripple counter, when you use that count pin to control the counting process. So the counter will increase by 1 at every clock pulse, so it can be either positive edge or negative edge. It's up to your design. And so it count until it hit 9, which is 1 0 0 1. Then repeat back from 0 0 0 0. So on a basic level, just same thing with binary ripple counter, just different number of states. So here I have a state diagram for you guys here. Okay, so the key concept is you need to have a present state and a next state, right? Now you want to analyze how thing is gonna change, okay? Depending on the input or depending on the previous flip-flop. So if the system is a negative edge, okay, so if the first flip-flop responds on a negative edge, so it responds when the count pin goes from 1 to 0, okay, you can see that then the first flip-flop Q1 will flip. The first flip-flop Q1 will flip every time the count input goes from 1 to 0. The second one also the same. Now you examine the Q4, okay, and I will talk about the Q2 and Q8 later because they will have some exception. Q4 is similar to Q1 because Q4 flip when Q2's, which is the previous flip-flop, when Q2's goes from 1 to 0. Okay, these two are easy. Now it's the hard one. Now Q2. So Q2 flip, let me point out the pointer. So Q2 flip when Q1 goes from 1 to 0. Only when Q8 equal to 1, equal to 0. So for the first whole, from this row to this row here, this apply. Q2 will flip when Q1 go from 1 to 0. Okay, 1 to 0 flip, 1 to 0 flip, right? 1 to 0 flip, 1 to 0 flip, 1 to 0 flip, okay. 1 back to 0 doesn't flip, okay. So you see it only flip when Q8 is 0. When Q8 equal to 1, it stay at 0, okay. So it stay at 0. In the last column, you have Q8, you stay at the same value, okay. So stay 0. So Q8 stay at the same value when either Q2 or Q4 equal to 0. So once again, Q8 stay at 0 when either Q2 or Q4 is equal to 0. Now Q8 will flip when, okay, Q8 will flip when two things happen. First, when both Q2 and Q4 equal to 0. So both of them have to be equal to 0. And when Q1 goes from 1 to 0. So there's two things right there. So now you see the first condition for Q8 to flip is when both Q2 and Q4 is 0, okay, I mean it's 1. So basically it's this scenario here is when both Q2 and Q4 is equal to 1. So now when that happens, okay, Q8 okay, so when you have both of this equal to 1, which is this scenario, and you have Q1 goes from 1 to 0, you have Q8 flip, okay, and also Q8 will be clear. So Q8 will be clear on the next transition of Q1. Okay, so that's 3 items to consider about Q8. So now we will go through the circuit of the binary ripple counter. Okay, so first of all, remember Q1 and Q4. Okay, there's Q1 and Q4. Yeah, Q1 and Q4 is pretty simple. All you need to do is flip it, right? So you hardwire logic 1 to both J and K for Q1 and Q4. Okay, pretty simple. So why hardwire logic 1 to Q1 and to both J and K for Q1 and Q4? Remember the properties of JK flip-flop. If both J and K equal to 1, you flip. If both J and K equal to 0, you hold. And you can, if it's not equal together, so either J equal to 0 or J equal to 1, you can force the output to be either 0 or 1. Okay, so now you know how to wire for Q1 and Q4. How about Q2 and Q8? So let's start with Q2 first because it's simpler. What does it say here? So the text here say when Q8 equal to 0 or when Q8 equal to 1. So when Q8 equal to 0, you want both J and K equal to 1, right? You know that K is always 1, okay? So now when Q8 equal to 0, okay, you can probe the complement output of Q8, which is QA naught. So QA naught of Q8 when QA equal to 0 is 1, right? So you can probe that and feed that to J. So when Q8 equal to 0, both J and K here will be equal 1, and it's gonna flip. But when Q8 equal to 1, this one will be 0, right? Right? So this one will be 0. That means J will be 0, and it will force Q2 to be 0. Okay. Finally, we will go to the case of JK, the case of Q8, sorry. So if you see the text here, so when both Q2 and Q4 equal 1, so the easy way is you probe the output of Q2 and the output of Q4, you run it to an AND gate, you inject that into the J input. Okay, so when both of this equal 1, J will be also 1, and it's gonna flip. Okay, so if not, it will stay at 0. Okay, piece of cake. Finally, multi-decade counter. So the BCD counter that we discussed, it counts from 0 to 9. So it's a 1 decade or a single decade counter. So if you want to count from 0 to 99, it's 2 decades. So you need 2 BCD counters. Okay, I think you get the idea. If you want to count from 0 to 10 to the n minus to the n, then minus 1, it will cover n number of decades. So you need n number of binary counters, BCD binary counters. So here it is an example of 3 decades counter. So you can construct multiple decade counter by using multiple BCD counter. Okay, so the difficult one is over. Now is the easy one. Synchronous counters. So synchronous counter, remember the first example we went through? Basically, we have the state diagram and we go through the whole process of building a state machine. Okay, it's not some trick that you have to scan from one column to another column. It's more intuitive. But the only tricky part is similar to registers. So you have to make sure all of the flip-flop are synchronized with the same clock. Otherwise, all of your operation is gonna be totally messed up. Okay, so key thing here is you need the clock, and the clock, the synchronism of the clock and all of the flip-flop have to be controlled well. So you can design a synchronous counter with D flip-flop, JK, T flip-flop. In the first example, we went through T flip-flop, but literally, as I explained in the design process, when you draw the present state and next state, the next column is the flip-flop input column. You can decide like whatever input like flip-flop you want to use. So there's a lot of type of synchronous counters. There's binary. Okay, that means you just count in binary, like up by 1, like the first example that we do. There's up and down binary. There are BCD also. Just and up to your imagination. Okay, so let's go through one example. So T flip-flop is pretty common when you make counter, because the key function of T flip-flop is flip, right? Like basically flip the value. So when you count something in binary, you actually notice that the bit just flip, right? It either go from 0 to 1 or 1 to 0. So that's the key of counting. You can have the clocks placed into each clock input of every single flip-flop. Okay. And you can have AND gate placed between every single T flip-flop. that take in Qi and Qi minus 1 and place their input into Ti plus 1. Each Q output is taken as the 2 to the i's place for the binary number. So just have the T flip-flop in here. You can make some counting circuit. Yeah, but if you want to understand the design process of this, go back to the first example. Go through all of the how can I say, go through all of the state transition. Okay. Another synchronous counter that we have is the up-down binary counter. So up-down binary counter is quite interesting. Okay, so you can basically count things up and count things down. So I don't know if you remember the quiz that I have when you have 4 different states and you control the speed of the motor. Is technically when I designed that quiz, I was trying to ask you to design a system that can speed up the motor or you can slow down the motor. Okay, so this system right here, the up-down binary counter, is pretty good for controlling like a binary state of maybe like a speed motor or something like that. But also you have, if you want to design it, go through the same process, draw out of the state diagram, build your state table, build the truth table for flip-flop input equation, then you can have your up-down binary counter in here. But the reason why in the quiz I didn't ask you guys to do both up and down, I do up and reset, is because it's going to be very complicated. So once again, you can use T-flip-flop to implement all of this. You can use AND gate and OR gate. Best way to figure out is just write down your, just go through the truth table, derive this for yourself. You can see very clearly. Okay, now we go through another type counter. So usually we count from 0, right? We're just cutting from 0, then we just increase until the limit and we go back to 0 again. Now what if I ask you, I don't want to count from 0, I want to count from 5, or I want to count from 10. So that means I want the ability of let's say, taking a number or prompt the user to give me a number to start with. So if I want to design a circuit like that, okay, now I can use the concept of parallel load. Then I can design a circuit that loading, so basically I can build kind of like a load registers to load in the value. Okay, so I can load in the value, and you can remember this load circuit here. I can load in the value, so I can assign on of the flip-flop value in here. Then I can initiate the count. So we can have other type counter, and this type counter basically is a normal counter, but what happened is this counter have some unused state. Okay, that means it will skip. So technically this counter will skip some certain value. This type counter can be developed with typical sequential circuit design using state diagram, same process. It can perform operation such as only count even or count odd or multiple of 2 or 3. So it's up to your imagination. As I say, when you work on a counter design, draw out the state, see what is your counting sequence is going to be. Each number is going to be a state. Work out that state transition. Build your present state, next state table. Make another column for the flip-flop input values. Derive the flip-flop input equation. Build your circuit. So this example is just a counter that skips 3 and 7. And this is the last counter that we're gonna go through. This one is called ring counter. So it's similar to normal shift registers, but the last output, okay, will tie back to the first flip-flop input. So I don't know if you remember, or you can go back to the registers lecture when I try to transfer registers A, value of register A, to value of registers B, but then I also trying to keep the value of registers A in existence. So in that exercise, I also do the same thing. I lead the output of the last registers back to the input of the first. I lead the output of the last flip-flop back to the input of the first flip-flop. But in here, instead of leading E, I lead E0. So it will give me some kind of flickering transitioning. So this type of counter is called switch tail counter, or another name is Johnson counter, ring counter. So the ring counter is where the flip-flop complement, which is this, is fed back into the first flip-flop inputs. So let's say if everything is 0, can you imagine if everything is 0, right? Everything is 0, start A0, B0, C0, E0. Then you will have E0 is 1, right? So if you have E0 is 1, now will be fed back to here. So you have 1. Okay, so you have 1, then 1. So you have 1, right? You have 1. So you have 1, you have 0, you have 0, and you have 0. And you keep moving, you have 1, 1, 0, 0. And you have 1, 1, 1, 0. Then you will have 1, 1, 1, 1. Then you will have 1, 0, and so on. So you can design a circuit that go around and have it keep looping. Okay. So this is called Johnson ring counter. And this is the end of our counter lecture. So we are at the very end of our semester already. So this is probably the last design component. So now we're at the end of our semester. So the plan for the rest of the semester, I have probably a couple weeks left. So my goal is trying to cover, so we just finished chapter 6, okay? So we'll try to cover the whole chapter 7. Then that will be it for our semester. Regarding the exam, I was thinking, I haven't made the exam yet, but I was thinking making the exam into two separate components. I can have some multiple choice quizzes, some multiple choice questions for the quiz. Then another component will be a take-home exam. Okay. Regarding chapter 7, since I don't think you will have a lot of time to practice, so for the take-home exam, I will build in an extra question as a design question in chapter 7, regarding chapter 7. So if you can complete the chapter 7 related question in the final exam, it will be count as an extra credit. Okay, so make sure that this is some kind of incentive for you to try to study until the last chapter of the course, but also give you some chance to improve your grade. Okay, hope you have a good one. Bye bye. I'll see you later.